Common and Natural Logarithms. Hello everyone. To begin, let's recall that in our previous subsection, we defined the logarithm in a general sense. To refresh your memory, for any given base b, the logarithm of a to the base b is simply the exponent x such that b to the power of x equals a. Now, while theoretically, the base b can be any positive number as long as it is not equal to 1, you will find that in the fields of mathematics and science, two specific bases are used much more frequently than others. These are base 10 and base e. Over the next few slides, we will explore these two in detail, starting with the common logarithm and then moving on to the natural logarithm. The common logarithm. Now, let's dive into the first of the two special bases we mentioned in the previous slide. When the base of a logarithmic function is 10, it is referred to as the common logarithm. To understand this more clearly, let's look at the definition. The common logarithm of a number x is simply the power to which 10 must be raised to obtain that number x. In mathematical notation, we write this as log base 10 of x. One very important practical point to remember is that in many textbooks and on most scientific calculators, if the base is not explicitly written, for example, if you see it written simply as log x, it is often assumed to be base 10. Keep this notation in mind, as we will see in the next slide how this specific logarithm is applied in the real world to measure pH levels in chemistry. Real-world application of common logarithm. Now that we have established the definition of the common logarithm, let us look at how this mathematical tool is applied in a real-world context. A primary example of this is the pH scale. In the field of chemistry, the pH scale is used to determine the acidity or alkalinity of a given solution. In the field of chemistry, the pH scale is used to determine the acidity or alkalinity of a given solution. What is interesting here is that the pH scale is directly based on the common logarithm, which, as we discussed in the previous slide, is the logarithm with base 10 of the hydrogen ion concentration, represented as H+ in brackets. To express this mathematically, we use the formula pH equals negative log base 10 of the hydrogen ion concentration. In the next slide, we will walk through a step-by-step example to see exactly how to use this formula to calculate a pH value. Step-by-step example for common logarithm. Now that we have discussed the theoretical formula for the pH scale, let us apply it to a practical example to see how the common logarithm works in a real-world scenario. Suppose we have a solution where the hydrogen ion concentration is 1 times 10 to the power of negative 5 moles per liter, and we need to determine its pH value. In step 1, we simply identify the given concentration. Here, the hydrogen ion concentration, represented as H+ in brackets, is equal to 10 to the power of negative 5. Moving to step 2, we substitute this value directly into the pH formula we discussed in the previous slide. This gives us pH equals negative log base 10 of 10 to the power of negative 5. In step 3, we simplify the expression using the power rule of logarithms. As a reminder, the power rule states that the logarithm of a base p raised to the power n is equal to n times the logarithm of p. Applying this here, we bring the exponent, negative 5, to the front of the logarithm. This results in pH equals negative 5 times log base 10 of 10. For step 4, we recall a fundamental property of logarithms. Since the base and the argument are the same, log base 10 of 10 is equal to 1. Therefore, our calculation becomes 5 times 1, which equals 5. As a result, the pH of the solution is 5. This example demonstrates how the common logarithm allows us to express very small concentrations as simple, manageable numbers. Now that we have mastered the common logarithm, let us move forward to explore the natural logarithm. The natural logarithm. Now that we have discussed common logarithms with base 10, let us move on to the second, most frequently used base in mathematics and science. When the base of a logarithmic function is the mathematical constant, e, which is approximately equal to 2.71828, it is referred to as the natural logarithm. To put this into a formal definition, the natural logarithm of a number x is the power to which the constant e must be raised to obtain that number x. In terms of notation, you will see this written in two different ways. It is most commonly denoted as ln x, or it can be written as log base e of x. Important note on notation for natural logarithms. Now, I want to draw your attention to a very important point regarding notation, as this is where many students often get confused. In higher mathematics, particularly when you move into calculus or follow the grade 12 NCERT curriculum, you will find that the notation log x is used interchangeably with ln x. This means that while we previously discussed that log x often refers to base 10 in basic textbooks, in more advanced contexts, it frequently refers to the natural logarithm. Therefore, for the remainder of this course, unless I explicitly specify a different base, whenever you see log x, you should assume that the base is the mathematical constant e. Real-world application of natural logarithm. Now that we have a clear understanding of what the natural logarithm is and how we denote it as ln x, let us look at how this is actually applied in the real world. A primary example of this is found in physics, specifically in the study of radioactive decay. Natural logarithms are essential here because they allow us to calculate the exact amount of time it takes for a radioactive substance to decay from its original state to a specific remaining level. To understand this, let's look at the formula for the remaining amount of a substance, which is written as n of t equals n naught times e raised to the power of negative lambda t in this expression. N of t represents the amount remaining at a given time, n naught is the initial amount of the substance, and lambda represents the decay constant. However, in many practical scenarios, we aren't looking for the remaining amount, but rather the time it takes for the decay to happen. To find the time, t, we must rearrange the previous formula using the natural logarithm to isolate the variable. This gives us the formula, t equals the natural log of n naught divided by n of t, all divided by lambda. As you can see, the natural logarithm is the perfect tool here because it allows us to undo the exponential base e, making it possible to solve for time. In the next slide, we will walk through a concrete example to see exactly how to plug numbers into this formula. Step-by-step example for natural logarithm. Now, let us apply the formula we just discussed in the previous slide to a practical example involving radioactive decay. Suppose we have a substance with a decay constant, lambda, equal to 0.1. Our goal is to determine the time, t, it takes for the initial amount, n naught, to reduce to half of its original size. In mathematical terms, this means the amount remaining at time t, or n of t, is equal to 0.5 n naught. Let us walk through this calculation step by step. In step 1, we need to set up the ratio of the initial amount to the remaining amount. We divide n naught by n of t, which is n naught divided by 0.5 n naught. Since n naught cancels out, this simplifies simply to 2. Moving to step 2, we substitute this ratio and our decay constant into the time formula we established earlier. This gives us t equals the natural log of 2 divided by 0.1. In step 3, we use the approximate value for the natural log of 2, which is 0.693. Substituting this into our equation, we get t equals 0.693 divided by 0.1. Finally, in step 4, we perform the division to find the final value. This gives us t equals 6.93 units of time. As we move forward to the summary, keep in mind how the natural logarithm allowed us to isolate the time variable in this exponential decay process. Key takeaways. Now that we have explored both the common and natural logarithms through real-world examples like the pH scale and radioactive decay, let us consolidate our understanding with these key takeaways. First, let's recap the common logarithm. As we discussed, its base is 10. In mathematical notation, we write this as log base 10 of x, although in many general contexts, it is simply written as log of x. Next, we have the natural logarithm. This is the logarithm where the base is the mathematical constant, e. This is specifically denoted as natural log of x, or log base e of x. Now, please pay close attention to this point regarding our course convention. While you may have seen log of x used to represent base 10 in previous years or other textbooks, in this grade 12 mathematics course, whenever you encounter log of x, you should assume the base is e. This is a standard practice in higher-level mathematics and calculus. Finally, let's consider the relationship between these functions. Both the common and natural logarithms are inverse functions of their respective exponential functions, namely 10 to the power of x and e to the power of x. This means they essentially undo each other. With these fundamentals clear, let us move to the final slide, where we will discuss some common mistakes to avoid so that you can apply these concepts accurately in your exams. Common mistakes. Now that we have covered the definitions and applications of both common and natural logarithms, let's wrap up this session by discussing some common mistakes to avoid. This will ensure you don't lose marks on simple errors during your exams. First, let's talk about confusing the bases. A very frequent error is applying base 10 calculations to a problem that actually requires base e. To avoid this, always analyze the context of the question. For example, if you are solving a calculus problem involving differentiation or integration, you can be almost certain that the base being used is e. Secondly, there is the issue of notation misinterpretation. It is common for students to believe that natural log of x and log of x are two entirely different functions. However, as we emphasized in our earlier slides regarding course conventions, in advanced mathematics, natural log of x, log base e of x, and log of x are all different ways of writing the exact same thing. Finally, be mindful of the buttons on your scientific calculator. This is where many practical errors occur. On most calculators, the button labeled log is programmed for base 10, while the button labeled ln is specifically for base e. Always double-check which base your problem requires before pressing a button to ensure your final numerical answer is correct.